Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is motor nameplate information. Our objective is to recognize the pertinent information displayed on a motor nameplate. This is an extremely useful source of data in finding an equivalent replacement motor during maintenance and repair procedures. Let's say no amount of black magic can resurrect the burned and smoking husk of the motor you've been assigned to service. The factory you work at is at a complete standstill until you return the machine this motor is responsible for running back to production. The obvious first step is to look up the motor's manufacturer and part number, check your own stock, or call the company directly and order an exact replacement. There could be some problems with this approach. Number one, you're out of stock. Lean manufacturing principles apply, meaning it is your company's policy to always be out of parts. Number two, the company that manufactured this motor exists, but no longer manufactures that exact motor. Number three, the company exists, but that motor is on back order or is otherwise not available for about 2 million days. Number four, the company exists, but the price of the motor went up tenfold just the day before you called. Or five, more often than not, the company no longer exists and was driven out of business by cheap overseas competition. These cheap overseas competitors offer a similar motor at 1/8 the price and 1/16 the quality, and the motor is made out of the compressed bones of U.S. factory workers and lubricated with their blood. None of these options seem appealing to you, so you've got to start doing your homework. The first reading assignment for this homework is the motor nameplate affixed to the damaged motor. Hopefully the nameplate is still readable. This is why a lot of motor nameplates are made out of metal. Not that motors are ordinarily given to bursting into flames, but rather metal nameplates are designed to withstand the test of time in a dirty industrial environment and remain readable provided no one paints over them. The motor nameplate is where you can find all the necessary data to find a similarly rated motor from whatever source that doesn't violate your code of ethics and ultimately plunge your country into financial ruin. Ideally, all manufacturers should ensure that information appearing on their nameplates is common to all other manufacturer nameplates, thereby enabling interchangeability. Should. Take note of the dramatic pause. Before you even think about reading the motor nameplate, you should first know what type of motor you're looking at. There's no sense in trying to find a comparable replacement DC motor when the device that failed was a 3-phase AC squirrel cage induction motor. The Motor Family Tree Lecture, available at the Big Bad Tech channel, discusses the means of classifying different types of motors. This lecture primarily deals with general motor nameplate characteristics, and the illustrated examples largely feature 3-phase AC squirrel cage induction motors, since this is the most popular industrial motor in the known universe. Later lectures will discuss the idiosyncrasies of other common motors. There is a lot of information out of the motor nameplate, but depending on how you look at it, each piece of data can be sorted into one of several bins: manufacturer information, electrical characteristics, or performance and physical characteristics. Additionally, there's optional data that is really nice to have, but doesn't always appear. This optional data could be binned into electrical or performance and physical characteristics, or be something totally off the wall in its own separate category. Depending on how you look at it, you could also categorize something as an electrical or performance and physical characteristic. The bounds between these categories aren't formal, and I'm only trying to divide the mountain of information up into manageable wheelbarrow loads for you to haul around. First and foremost on the information found on the motor nameplate is the manufacturer name, the model of the motor, and perhaps the serial number for that exact motor lying on the factory floor. The manufacturer is the company that made it, and it's a cheap form of advertising for them. Every time you walk through the factory floor, you see their logo. It enters your subconsciousness, and you're compelled to call them first, even though they may not offer the best deal. The model number is specific to that manufacturer and means only something to them and not any other manufacturer of similar motors. The model number is that manufacturer's means of coding that specific style of motor and is also useful for finding replacement parts for that specific style of motor from that specific manufacturer. The serial number, if it appears, is a unique identifier for that particular motor. Ideally, a manufacturer would be able to look up the serial number using their historical database and tell you when and where it was manufactured, whether it is or isn't under warranty, or whether the production run this particular motor was part of has any known faults or issues, like let's say a tendency to burst into uncontrollable flames. The manufacturer, model, and serial number is like your lazy lab partner's lame ride. Ford made it, It's a Festiva, the only car to comfortably seat half a human being, and the VIN number is 420 247 69 36 24 36 XXX. Manufacturer, model, serial number. No wonder you regularly choose to walk to class regardless of the weather. The next set of important information appearing on a motor nameplate pertains to the electrical aspects of the motor, namely voltage, current, frequency, phase, efficiency, power factor, thermal protection, connection diagrams, and something totally different than power factor, service factor. Voltage. If there is one aspect of the motor nameplate that kinda drives me crazy, is the means of how voltage is expressed. The nameplate voltage value is close to, I'm using quotation marks with my fingers by the way, to the nominal system voltage the motor is intended to run on, and you're supposed to know which system voltage that is. For example, a motor with a nameplate voltage of 115 volts is meant to be run on a 120 volt system. A motor with a nameplate voltage of 200 volts is meant to be run on a 208 volt three-phase AC system. As much as this mismatch between nameplate voltage and system voltage drives me absolutely nuts, there's a reason behind it, which stems from a NEMA requirement that a motor deliver its rated mechanical horsepower at plus or minus 10% of the nameplate voltage. This means a 1 horsepower motor with a nameplate voltage of 200 volts should be able to deliver the desired 1 horsepower or 746 watts at 180 volts or 220 volts. The slightly lower nameplate voltage value ensures that the motor has enough punch when it's hooked up to the higher nominal system voltage of 208 volts. Even understanding this requirement, it still drives me nuts. Be aware that for a three-phase AC system, the motor nameplate voltage is the line-to-line voltage between any two phases of the three-phase AC system, and it is not the line-to-neutral or phase voltage. A motor designed to run on a 120 volt line-to-neutral or 208 volt line-to-line three-phase AC system would have a nameplate voltage of 200 volts. This would go for motors wired in either delta or Y configuration. Notice each winding in the Y configuration would only see the line-to-neutral or phase voltage of 120 volts, whereas each winding in the delta configuration would see the line-to-line voltage of 208 volts. Again, motor nameplate voltage is the line-to-line voltage between any two phases of the three-phase AC system. We'll discuss how this affects electrical power calculations in a moment. Also be aware that there may be two ratings in the voltage entry. This means that this motor is a dual voltage motor, and pending proper use of the connection diagrams, which we'll get into later, this motor could be wired for either a low voltage configuration or a high voltage configuration. An example of this might be for those of you with a well pump in the United States that could be wired for a single phase 240 volts AC or single phase 120 volts AC. For those with an understanding of power computations, it's immediately recognizable why the high voltage, low current configuration is preferred when you consider the cost per foot of thicker wire necessary to run the lower voltage, higher current configuration. We'll examine dual voltage motors and motor connection diagrams in a later lecture. Speaking of current, let's talk about current. The rated current on the motor nameplate is that line current drawn by the motor when the motor is operated at rated torque, sometimes called full load torque, or FLT on the torque speed curve. Hence the alternate name for this rated current is FLA, or full load amperes. If one loaded the motor less, the observed line current will be less than FLA. If one loaded the motor more, the observed line current will be more than FLA. Current draw in excess of FLA would be known as an overload condition. Momentary overloads aren't ordinarily an issue. However, sustained overloads produce excessive heat and may damage the motor insulation over time. It is for this reason a motor starter incorporates not only a means of making and breaking a connection to a motor, called a contactor, essentially a high voltage switch, but also a means of protecting a motor from sustained overload conditions, called an overload relay. We'll discuss contactors, overloads, and motor starters in later lectures. Most of the data in the motor nameplate is referenced from this single snapshot on the torque speed curve and assumes the motor is being operated at rated torque and rated speed conditions. This is ideally where you'd ordinarily run this motor. In the case of motor nameplate current, this is the current draw at that point on the torque speed curve. One would think conductor size supplying this motor would be based off this nameplate current rating, but it's not. There is a significant safety factor involved, and current values are assigned to specific motor power sizes as per National Electrical Code Article 430, Motors, Motor Circuits, and Controllers. Trust me, you do not want to listen to a lecture on NEC code as much as I do not want to give one. I am not an electrician, and you cannot use anything you learn from this or any of my other lectures as professional electrical advice. Follow the rules. Follow the code. It's there for a reason, to safeguard people and property from electrical and fire hazards. Sometimes you'll see two nameplate current ratings for dual voltage motors. Obviously, one is for the high voltage configuration, the one with a low current, and the other is for the low voltage configuration, the one with a high current. Again, we'll examine dual voltage motors and motor connection diagrams in a later lecture. Similar to the clarifications I issued regarding motor nameplate voltage, the motor nameplate current is the line current, regardless if the motor is wired in delta or Y configuration. Notice each winding in a Y configured motor would experience the line current, whereas each winding inside a delta configuration motor actually receives less than the line current because of the 120-degree offset between phases. By using the line-to-line voltage and line current, regardless if the motor is wired in delta or Y configuration, it allows a technician to measure voltage and current outside of the motor and prevent unnecessary, time-consuming, and invasive inspection of either line-to-neutral voltage for a Y-configured motor or phase current for a delta configuration. Trust me, these measurements are not fun, nor are they easily obtained for all motor configurations. Regardless, a simple manipulation of the two comparatively easily obtained values of line-to-line voltage and line current can be used to determine electrical power requirements for a balanced three-phase AC load like a motor. For those with an understanding of apparent power calculations for balanced three-phase AC loads, you'll recall that it can be calculated as square root 3 times line-to-line voltage times line current, regardless if the motor is wired in a delta or Y configuration. Speaking of power, why have I not included the nameplate power in the electrical characteristics group? You'll soon know the answer. Anticipation, as they say, is part of showmanship. Phase and frequency obviously refer to the type of AC, single-phase AC or three-phase AC, and the frequency of the AC system this motor is intended to run on. All the other data on the motor nameplate is based off this fact. A 50 Hz motor with a rated speed of 1,460 RPM won't spin at 1,460 RPM when operated at 60 Hz, but rather around 1,750 RPM. Power factor is a ratio of how much power apparently delivered to the motor is available for conversion into real output power, the rest being reactive. Notice the terms I'm emphasizing: apparent, real, reactive. Those with an understanding of AC power will realize that the vectorial combination of real, P, and reactive, Q, is apparent power, S. The power factor is the ratio of real over apparent, or the cosine of the angle between that of voltage and current. Motors are inductive loads, and obviously current will lag voltage. The power factor on the nameplate is a snapshot at full load conditions and will vary considerably over the operational range of some motor configurations. We'll learn in later lectures that motors like the three-phase AC squirrel cage induction motor can have extremely low power factors when unloaded, since they must consume reactive power to generate a magnetic field. However, phase shift between voltage and current decreases, and power factor notably increases as the motor is loaded up to rated conditions. This means more real power is available for conversion into mechanical output. Efficiency is that portion of real input electrical power in watts that is successfully converted into output mechanical power in watts. Losses include heat, friction, and other sources. The efficiency rating on the motor nameplate is again a snapshot at full load conditions and will vary considerably over the operational range of some motors. Have you figured out why I've not included the motor nameplate power in the electrical characteristics group yet? There's a hint hidden in this last section. You may wonder why I've included thermal protection in the electrical characteristics group and not the physical characteristics group. The reason is that this entity, if it appears on a motor nameplate, specifies whether the motor has built-in thermal overload protection that electrically disconnects the motor from the supply voltage after sensing a sustained overload condition. In this case, it's like the motor has its own built-in overload contacts. Connection diagrams are pictorial representations of the wiring configurations for different voltages if the motor is dual voltage, or different speed characteristics in the case of multi-speed consequent pole or multi-speed separate winding motors. This entry on the motor nameplate necessitates another independent lecture since it's pretty important. If you're following the motors and generators playlist in its intended sequence, it's most likely in close proximity, so I need you to remain poised in a cat-like state of alertness until then. Long story short, you get 0 points for creativity. Follow the connection diagrams exactly as illustrated, otherwise serious repercussions may result. As we'll discuss in the electromagnetic interaction lecture, polarity of the magnetic field is dependent upon current direction, and a motor might be damaged or at the very least not work well if it isn't properly wired. Again, the upcoming motor connection diagram lecture will deal exclusively with this aspect of the motor nameplate. Let's wrap up the electrical characteristics found on the motor nameplate by discussing service factor and then move on to physical and performance characteristics. Service factor sounds like power factor, but it's something totally different. Service factor is the degree to which one can continuously overload this motor beyond its rated capacity. A cheap service factor 1 motor can't be overloaded. However, a well-designed, beefy, and expensive service factor 1.25 motor can be overloaded by 25% without overheating. Next batch of important information found on a motor nameplate is performance and physical characteristics, namely power, speed, frame size, enclosure, ambient temperature, temperature rise, insulation class, duty cycle, inverter or vector duty, code, and design. Power. Multiply voltage times current and you obtain power in watts. Yes, true for DC and with some slight modifications for single-phase and three-phase AC, but not really. The power referred to on the motor nameplate is output mechanical power. Rotating mechanical power is the product of a twisting force called torque, T, times rotational speed, N, and dividing by a constant appropriate to your units. In the case of torque in units of Newton meters and rotational speed in units of revolutions per minute, this constant is 9.55 and your output mechanical power is in watts. If you have mechanical output power in watts, you can divide this by 746 to obtain the power rating in horsepower, because 1 horsepower equals 746 watts. Motors below 1 horsepower are sometimes called fractional horsepower motors, because they're obviously delivering a fractional value of a horsepower. For example, a 373 watt motor is a half horsepower motor, equivalent to maybe a pony or a horse with only 2 legs. We'll discuss rotating mechanical power in greater detail in the mechanical power, torque, and speed lecture. The electrical power we referred to earlier needs to jump through 2 important hoops to yield this usable mechanical power. These hoops are power factor and efficiency, other pertinent pieces of information already included on the motor nameplate. Since electrical power input and usable mechanical power output are inextricably related via power factor and efficiency, let's take a moment to discuss this relationship. For some of you, this might be a review. Others might find this totally new material. You can calculate input electrical apparent power at full load conditions using the motor nameplate voltage and current ratings. To calculate real electrical power available for conversion to mechanical power, one would use the power factor. To calculate that portion of real electrical power that actually does get converted to mechanical power, one would use the efficiency rating. For example, consider a 3-phase AC motor rated for 460 volts that draws 450 milliamperes at rated conditions. The motor nameplate additionally states that it is a quarter horsepower motor, a one-legged horse or half a pony, that rotates at 3,420 RPM and has a power factor of 0.85 and a 62% efficiency at rated conditions. Using the rated voltage and current from the motor nameplate, we can calculate that this motor would be consuming approximately 358.5 volt amperes of apparent power. To calculate real electrical power available for conversion to mechanical power, one would use the power factor from the motor nameplate. This means that the motor would be consuming approximately 304.8 watts of real electrical power. Those well versed in AC power will also note it is consuming 188.9 VARs of reactive power. Note the vectorial, not the algebraic, summation of 304.8 watts of real electrical power and 188.9 VARs yields approximately 358.5 volt amperes at an angle of 31.8 degrees, or the inverse cosine of 0.85. To calculate that portion of real electrical power that actually does get converted to mechanical power, one would use the efficiency rating from the motor nameplate. This means that this motor would be delivering approximately 188.9 watts of mechanical power. Let's check to make sure this makes sense. Power in should equal power out. The motor nameplate says that this is a quarter horsepower motor, meaning it delivers 746 watts divided by 4 of usable mechanical power. 746 over 4 equals 186.5 watts. I'd say this nameplate is correct to a reasonable degree of accuracy. Additionally, if you've got an understanding of mechanical power as a function of torque and rotational speed, one can also back calculate the rated torque produced at the rated speed if it's not included on the motor nameplate. Mechanical power in watts equals rotational speed in units of RPM times torque in units of Newton meters divided by the constant 9.55. Solving for torque and substituting in the necessary values, we find this motor delivers approximately 0.5208 Newton meters of torque at rated conditions. If you think about torque and speed and their relationship with mechanical power, you realize this motor is designed to go pretty fast, but has relatively low torque output. Either way, it's delivering approximately 186.5 watts or a quarter horsepower of mechanical output. If one desired higher torque, one could potentially use a step-down gearbox intermediary to step down the rotational speed and proportionally step up torque minus losses. Again, we'll discuss mechanical power and its relationship with torque and rotational speed in later lectures. However, the point is that a motor nameplate is essentially an open book if you know how to read it. Given rated voltage and current and power factor, we calculated apparent and real electrical power input. Then we used efficiency to correlate this electrical input to usable mechanical output. Another take-home point about this diversion is this: if a motor has a low power factor and poor efficiency, what you really get out of it is a lot less than what you're apparently putting into it. Other lectures at the Big Bad Tech channel discuss AC power in greater depths, as well as all the cunning ways power factor can be corrected, such that real power delivery is the same, yet line current is less. Speed obviously refers to the rotational speed of the shaft at full load conditions, and is ordinarily measured in units of revolutions per minute, or RPM. As we'll learn in later lectures, the rotor of a three-phase AC squirrel cage induction motor, the most popular industrial motor in the known universe, must necessarily lag behind the natural speed of the rotating stator magnetic field, even under no load conditions. The natural speed of the rotating stator magnetic field is known as synchronous speed and is a relationship of input AC frequency and the number of pole pairs per phase. Given the rotor already rotates slower than synchronous speed for unloaded conditions, one would expect at full load conditions the speed would be even less than this unloaded speed. Again, the data on a motor nameplate is a snapshot at full load conditions. If you really wanted the whole speed torque curve for a given motor, you'd have to look it up on this thing called the internet. Perhaps you've heard of it. Frame size obviously refers to the mounting dimensions and type necessary to properly secure the motor. There are NEMA and IEC frame charts available for cross-referencing the size of every hole you need to drill and the distance between each hole and more. Enclosure is a means of describing whether the motor is open or enclosed. The level of openness versus enclosure is a spectrum, with totally naked at one end and the NORAD Cheyenne Mountain nuclear bunker at the other end, as dictated by the operational environment. Not all situations require a totally enclosed, explosion-proof enclosure, but for those that do, it's probably not a good idea to just grab a splash-proof open enclosure off the shelf and get her done. Your town may be saddened to hear the loss of an entire coal mine of workers that died in a coal dust explosion ignited by your stupid shortcut. While we're on the subject of enclosure, both motors that are open or fully enclosed need a means of keeping cool and sometimes include fans, heat dissipating fins, blowers, and even water coolers to do so. If you're working in a sawmill or a flour mill or some other environment that's dusty and dirty, low-level maintenance often takes the form of simply keeping things clean. Given heat degrades components, imagine working in an already hot environment wearing a quilted jacket stuffed with 3 inches of sawdust all day long. Keeping motors clean is a valid maintenance task that ensures the long life of your equipment. Speaking of heat, let's talk about ambient temperature and temperature rise. Ambient temperature is the maximum recommended environmental temperature in case the motor needs to be outside in full sun or inside a hot industrial environment. Temperature rise, if it appears on the motor nameplate, refers to the rise above ambient at full load conditions. This is good information to know if other thermally sensitive electrical equipment is in close proximity to the motor. Insulation class refers to the lifespan of the insulating material given certain operating temperatures. All else being equal, the higher the insulation class letter, the longer it's going to last at higher temperatures. It'd be a super bad idea to swap out a motor with an insulation class H for one with a poor insulation class A and expect it to haul an elephant onto a black rooftop in Arizona on the 4th of July. Duty cycle refers to the frequency the motor is expected to be run. If the motor is designed to operate all day, it would be a continuous duty cycle motor. Whereas if it was designed to run only every once in a while, it would be an intermittent duty cycle motor. An intermittent duty cycle motor really is designed around the fact that it will be allowed a chance to cool off between uses and not just ceaselessly haul a whole herd of elephants onto the roof without rest. The inverter or vector duty entry, if it appears, designates the motor as being an inverter duty or vector duty motor. This entry is related to both insulation class and duty cycle, and if you think about it, pretty much everything else on the motor nameplate. This means the motor has been purposely designed to work with a motor drive, sometimes called a variable frequency drive or VFD. A VFD is a power electronics device we'll discuss later that can vary motor output speed and torque by varying input frequency and voltage. Given everything else on the motor nameplate has been based off a constant supply frequency and output speed, it'd be understandable that a motor designed to operate at different speeds should be purpose-built. For example, a motor running at a slower speed wouldn't spin its cooling fan as fast and would probably heat up more. Therefore, the insulation class should probably take this into account. If your motor can handle this task, it'll say so. Motors older than dirt, yes, some of them are still running and you're going to have to fix them, obviously won't say this and are probably due for an update anyways. VFDs are becoming increasingly cheap and available and have numerous cost savings benefits. Code and design, the last 2 remaining items on our motor nameplate checklist, are very easily confused terms. To make matters worse, sometimes people call design code. To make matters much worse, both code and design use letters. I don't like this any better than you, so deal with it. Code refers to a means of estimating inrush current. Inrush current is the initial surge of current when you first turn on a motor. This is often known as locked rotor conditions. This initial current surge can be several times as large as expected current for full load conditions and must be accounted for. The general ballpark figure is 6 times full load conditions. Luckily, inrush conditions don't last for long, and once the rotor comes up to rated speed conditions, the current levels out. The letter refers to a chart where for each letter there's a range of constants for kilovolt amperes per horsepower. You can estimate inrush current by using the constant in this calculation. where for a three-phase AC motor, the code constant times the motor horsepower divided by rated voltage is multiplied by 577 using the appropriate input units. If this is a single-phase AC motor, 577 is replaced by the constant 1000. Notice that there's no I, O, or Q code in our locked rotor code letter chart, and notice it stops at V. It's a trick question if the motor nameplate code features letters outside this chart. Also, if you're having a hard time reading the motor nameplate because some dummy painted over it, you can at least exclude these possibilities. For example, consider a 50 horsepower motor rated for 460 volts with a code G. Code G represents a constant of 5.6 to 6.3 kilovolt amperes per horsepower. So let's aim for center of mass and say it's 5.95. Substituting these values into the equation, you would expect to see an inrush of 373 amps. For reals. The rated current for this particular motor is 61 amps, and this is in the range of the 6 times rated current ballpark figure you'd expect to see. Inrush current thankfully doesn't last for long, but you definitely got to take into account an expected surge of 373 amps when starting this motor. Design letter refers to the shape of the torque speed curve. Design B is the most common, but sometimes you'll see design D for motors designed to lift loads with large static inertia. The elephant elevator example would be a good place for one. Notice this graph features torque as a percentage of full load torque. A design letter B can move a load from a dead stop only slightly higher than its full load torque. However, design D can move a static load at almost 300% of its rated torque. Obviously, this comes at a price, and the torque drops significantly with increasing speed. The differences between these designs are primarily due to increased rotor resistance for the D designs. This about wraps it up for the tour of the motor nameplate. Again, expect to find more or less data in all sorts of different languages and in no particular order. At the very minimum, you should be able to get the manufacturer and model number and the voltage this motor was intended to operate on, and then use this thing called the internet, perhaps you've heard of it, to find the particular piece of information you're looking for. Let's put your newfound knowledge to the test and see if you can decipher the information found on some real motor nameplates. First, let's check out the motor nameplate affixed to these vaguely phallic-shaped pump motors. This is a beautiful example of pretty much everything a motor nameplate should be, and no knucklehead painted over it. It does contain some subtle deception though, principally its manufacturer. These motors have the US Motors symbol embossed all over them, and no less than 3 stickers announce US Motors in bright, eye-catching colors. The manufacturer, as you would expect, is US Motors. Made in Mexico, owned by Nidec of Japan. US Motors is not a company anymore. It's a brand. Be aware of such transparent marketing sleight of hand. The model number is actually the catalog number. Be aware of different terms that mean the same thing. The catalog number is actually HO50S2SLG when you look it up on the US Motors, a brand of the Nidec Corporation website, but the O looks like a 0. In addition to painted over motor nameplates, be aware of just plain hard to read motor nameplates, especially motors that have been sitting outside directly exposed to sun and rain. The serial number is this string of nonsense right here. I expect this means something to the right people. This motor is designed to run on 60 Hz, 3-phase AC at a rated voltage of 460 volts. The system voltage would be 480 volts. The frame is 326 TP. You'd have to look up the dimensions on the US Motors, a brand of the Nidec Corporation website, to find shaft diameter, center to foot dimensions, etc. The enclosure is WP1, which is weather protected type 1. Obviously a good choice since it's outside. Openings minimize entrance to rain, snow, and other airborne particles. The maximum ambient temperature you can use this motor at is 40 degrees Celsius. The output mechanical power is 50 horsepower. No wonder this motor is so big. The rotational speed at the rated output is 1,775 RPM. It's a continuous duty cycle with a power factor of 0.85. There's 2 efficiency ratings, 90.2% and 88.5% depending on how you look at it. It has a service factor of 1.15. Its rated current is 61 amps, and its locked rotor code is G. If you remember correctly, we calculated inrush using these exact figures and determined it to be around 373 amps. Looks like our design code is B, which dictates the shape of the speed-torque curve. If you visit the US Motors, a brand of the Nidec Corporation website, you can actually download the datasheet for this particular motor, which includes a number of handy graphs including the speed-torque curve on page 3. We'll revisit this data in later lectures on three-phase AC squirrel cage induction motors. There's a bunch of other information regarding weight of the motor, oil capacity, grease, and bearings. All in all, this is a great motor nameplate. Our last example is not a great motor nameplate, principally because someone painted over it. You thought I was joking this whole time, didn't you? This really happens. If you squint real hard, you can probably figure it out because of the raised lettering, but the fields in which the raised lettering appears are pretty legible. Don't strain your eyes too hard because luckily there's an identical motor right next door that somebody didn't paint over. You get some pretty generic information. It's designed to operate with 3-phase 60 Hz AC and has a locked rotor code of F. Its mechanical power output is 25 horsepower at a rated speed of 1,765 RPM. It's a continuous duty cycle with an installation class B, which is kind of hard to read. Has 1.15 service factor, design letter B. The frame is a 284 HP, has a maximum ambient temperature of 40 degrees Celsius. It's a Westinghouse model TBDP. It has 2 voltage entries at 230 and 460 volts, and its rated current is 32.5 amps. The interesting point about this motor nameplate is the connection diagrams for low and high voltage. It's a dual voltage motor. Those with understanding of motor connection diagrams will realize that this is a delta configuration motor. For those that have yet to watch the motor connection diagrams lesson, let this serve to stimulate your thinking. Motor nameplates are everywhere if you know where to look, and reading them is kind of a fun game. I'm encouraging you to poke around your school, your lab, and other industrial settings to test out your newfound skills. Who knows, you might learn something. Or maybe you'll get arrested for trespassing. Split up, run fast, tell them nothing. In conclusion, this lecture discussed the pertinent information found on a motor nameplate. This information is extremely helpful in finding an equivalent replacement motor during maintenance and repair procedures. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.